morning, Manandal. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in today's lecture, we are going to solve some of the problems based upon transmission lines in electromagnetic waves and transmission lines. So, to solve some of the problems based upon this transmission lines, first, we are going to recollect some of the formulas related to this transmission lines to solve the problems which we have considered in this particular lecture. So, first problem is based upon a telephone line has R equal to 30 ohm per kilometer and L equal to 100 millihenry per kilometer and G equal to 0 and C equal to 20 microfarad per kilometer. So, the transmission line primary characteristics or primary parameters of a transmission line R, L, G, C values are given, that is R equal to 30 ohm per kilometer and L equal to 100 millihenry per kilometer, then G equal to 0 and C equal to 20 microfarad per kilometer, and the signal frequency f equal to 1 kilohertz is given. Right? So, based upon this RLGC primary constants of a transmission line, resistance, inductance, conductance and the capacitance, we are going to solve here the characteristic impedance of the transmission line, that is denoted with Z0, and the propagation constant of a transmission line, that is denoted with gamma, and the phase velocity nothing but Vp. Right? So, in order to solve all three parameters, that is characteristic impedance of the transmission line, then Z0 in terms of all the means the secondary constant of a transmission line, which is expressed in terms of primary constants of a transmission line, that is Z0 is equal to root over R plus j omega L into G plus j omega C. So, in terms of all the primary constants, and it consisting of operating frequency of a line also, that includes omega. As the given value f is given, that is 1 kilohertz. Now, the relation between omega and f is given by omega equal to 2 pi f, and it is nothing but 2 pi into f value is 1 kilohertz, 1 into 10 cube, okay, which is equal to 2 pi into 10 cube is the value of omega, and it is given by radian per second. Then, propagation constant gamma. The formula now to solve this propagation constant gamma, that is, here this is the formula for gamma propagation constant, and here if you find the value of characteristic impedance, means Z0 is equal to root over R plus j omega C by G plus j omega C. So, the propagation constant of a transmission line is given by here gamma, which is equal to root over R plus j omega L into G plus j omega C, whereas the characteristic impedance Z0 is given by root over R plus j omega L by G plus j omega C. Right? So, where gamma and Z0 are called as secondary constants of a transmission line. Right? So, the characteristic impedance of a transmission line in terms of all the primary constants along with the operating frequency, that is Z0 is given by root over R plus j omega L by G plus j omega C, and the propagation constant gamma can be written by the mathematical equation as by including all the primary constants and the operating frequency as root over R plus j omega L into G plus j omega C. Right? So, then substitute all primary constant values which are given in the problem, that is R equal to 30 ohm per kilometer, L equal to 100 millihenry per kilometer, and G equal to 0 and C equal to 20 microfarad per kilometer. Right? So, at f value is also given, that is 1 kilohertz. Now, from this f, we will be evaluating the value for angular frequency as omega. Nothing but omega equal to 2 pi f. If we substitute f by 1000, then 2 pi into 10 cube radian per second is the value for omega. And we know that phase velocity, that is defined by here Vp, nothing but is the ratio of omega to the beta. Velocity equal to omega by beta, and from this the propagation constant which constitute attenuation constant alpha and the phase constant as beta. Now from this we are going to get the complex impedance value. Now from this complex impedance we will be evaluating the real term as alpha and the imaginary term as beta. Now from the imaginary constant we will be getting the value of beta, and this value need to be substituted over here to get the value of phase velocity. Okay, so to solve this, first see the propagation constant we need to find first. So first one is gamma equal to, or before gamma equal to r plus j omega l into g plus j omega c and root over. Okay, so from this gamma equal to, so if you substitute RLGC values and omega value in the from the given, that is 30 ohm per kilometer, then 30 plus j into 2 pi into 10 cube into omega value, and L value need to be 100, that is from the given 100 millihenry per kilometer. 100 into 10 power minus 3, this is the total value which is to be between r plus j omega l into g plus. G value is to be 0 is given, then 0 plus j into omega means 2 pi into 10 cube into. And C value is to be as 20 microfarad per kilometer. 20 micro means 10 power minus 6 per kilometer is given, then this is the value to be g plus j omega c. Then root over this total thing is to be substituted. Then we can separate from this real and imaginary terms by multiplying the two terms with each other. Hence gamma equal to 30 into 0 becomes 0 plus 30 into j means j, then 20 and 30 if you multiply, then 2 3s are 6 and 0 becomes here already 10 power 3 is there, that becomes 10 power 5 into 10 power minus 6 into 2 pi. See 30 into 20, 3 2s are 6 and 2 pi, and 10 power 3 into 10 square becomes 10 power 5 into 10 power minus 6, that is j value, and then 30 into these two becomes the second thing, and this one is multiplied with this thing means j into this becomes 0 and j into j becomes j square, its value as minus 1. So minus, and 2 pi into 2 pi becomes 4 pi square, and 10 power 3 into 10 power 3 becomes 10 power 6, and into 10 100 is there, for that we can write it as 10 power 8 into, and here this 10 power minus 3 is multiplied with this thing as 10 power minus 9, and 20 is extra factor, that is here this also becomes 9, and into 2 is separate thing, right? So from this we will be getting the value gamma equal to, now from this 2 into 6 becomes 8 j 8 pi, so 2 2s are 6, 12 j 12 pi, and 10 power minus 5 into 10 power minus 6, then it becomes 10 power minus 1 and minus, and 2 4s are 8 pi square, then 10 power plus 9 and 10 power minus 9 gets cancelled, then minus 8 pi square is left out, then which is nothing but this. Then gamma equal to real term as minus 8 pi square plus j 1.2 pi is to be obtained, right? So in order to evaluate this one, we need to multiply pi by 3.18 value, and from this we will be getting the value as alpha as the real term and the beta as the imaginary term. So from this alpha need to be evaluated, and its value is to be given as alpha, that is 2.121 into 10 power minus 4 plus j into 8.888 into 10 power minus 3. So this is the value for alpha, and here it is given by beta. Why? Because as we know that gamma can be constitute attenuation constant alpha and the phase constant as beta, right? So from this alpha value is 2.121 into 10 power minus 4 and beta value is 8.888 into 10 power minus 3. And similarly, for the first part, means characteristic impedance of the transmission line is to be considered as here. See, Z0 is equal to the formula for the characteristic impedance of a transmission line. It is given by root over R plus j omega L by G plus j omega C. Okay, so R plus j omega L means R value need to be given as here. R is 30 plus j omega means 2 pi into 10 cube into L value is 100 milli, that is 10 power minus 3, by G value is 0 plus j omega means 2 pi into 10 cube into capacitance value is 20 microfarads, means 20 into 10 power minus 6, that is under root. Okay, so Z0 is equal to, evaluate the complete equation, then 30 plus j 10 power 3 and this 10 power minus 3 gets cancelled. 2 pi into 200 means j 200 pi by this 0 plus j into here 10 power 3 into 10 becomes 10 power 4, and here it will be means j 2 pi into 2 is 4 pi, then 10 power 4 into 10 power means 10 power minus 2, and 20 if you multiply 2 into 2 becomes 4 pi, 10 cube into 10 becomes 10 power 4, and into 10 power minus 6 becomes 10 power minus 2, which is given as Z0 is equal to root over 30 plus j 200 pi by j 4 pi means j 0.04 pi value is to be obtained. So in order to find the characteristic impedance value based upon the means impedance is generally measured in it's a complex value, real term and followed by imaginary term need to be explained then expressed. So that's why first, in order to get the real and imaginary terms, first convert this 30 plus j 200 pi into complex polar form as r1 at an angle of theta 1. You simplify if you convert it into polar form, and in the denominator part also r2 at an angle of theta 2 need to be obtained, and root of this thing. So root of means root of r1 by r2 means magnitudes of the numerator as well as the denominator need to be found. Now at an angle of means the theta 1 minus theta 2 root over, which is equal to, so root of this thing becomes r at an angle of means root theta formula, as we know that root theta can be written as theta by 2. Now from this theta need to be obtained. By subtracting theta 1 to the theta 2, we will be getting the value as theta, and root theta means formula becomes theta by 2. So from this Z0 can be written as obtained as polar form of r, and the phase angle can be written as like this. Now again from this we will be converting this into rectangular form, means the real term as alpha and the imaginary term as beta need to be obtained. Right? So if you evaluate like this, the characteristic impedance of the transmission line can be expressed as real term as 70.75 at an angle of minus 1.367 ohms. Sometimes we might be expressed the characteristic impedance as a complex form or rectangular form, means real and imaginary forms also. Here we'll be having the real term as means magnitude as r, and then at an angle of theta need to be obtained, where r value is 70.75 and at an angle of minus 1.367 degrees need to be obtained. As we know that characteristic impedance means impedance is generally measured in ohms, and it should be written as here 70.75 at an angle of minus 1.367 degrees need to be obtained as a value of characteristic impedance. Similarly, third case is for the velocity. Suppose if you consider any one of the value, see I am considering here the beta value need to be 8.888 into 10 power minus 3. See, now to find the phase velocity Vp, that is the formula omega by beta, and omega value need to be 2 pi into f value as 1 kilohertz is given, hence 10 power 3 by beta 8.888 into 10 power minus 3 need to be obtained. See, from the given 8.888 into 10 power minus 3 is the value of beta. So to find the phase velocity here, we'll be using the formula as Vp equal to omega by beta, then 2 pi into 10 cube by 8.888 into 10 power minus 3. So if you simplify this thing, 2 pi by 8.888 into 10 power minus 3 into, if you take this 10 power minus 3 into numerator, already 10 power 3 is there in the numerator, then it becomes 10 power 6. Then Vp is to be expressed into meters per second. And this is the value has got here 7.069 into 10 power 5 meters per second. Right? Or if you want to express the total thing into mega, also 0.7069 means like that we are going to express. Right? So if you in the problem the primary constants of a transmission line, that is RLGC values are given, then how we are going to evaluate the characteristic impedance and the propagation constant from that phase velocity, how we have been calculated with the help of formulas. As first formula, that is propagation constant gamma equal to root over r plus j omega L into g plus j omega C, and whereas Z naught, characteristic impedance Z naught, can be written as root over r plus j omega L by g plus j omega C, and from the third part, phase velocity, to calculate Vp equal to omega by beta. Right? So next, then one more problem based upon again transmission lines. So a 30-meter long lossless transmission line with Z0 equal to 50 ohms. A 30-meter long lossless transmission line with Z0 equal to 50 ohms operating point at 2 megahertz is terminated with a load ZL is equal to 60 plus J40 ohms, and if U equal to 0.6 into C on the line, then find the reflection coefficient gamma and the standing wave ratio as S and input impedance Zin need to evaluate. Right? So from the given, first we'll be identifying what is the given data. So first of all, the given data. How we are going to identify means from the given 30-meter long means L, the length of the transmission line is given, that is 30 meters. With the Z0, characteristic impedance Z0 is given, its value is 50 ohms. And the operating frequency means F is given, that is 2 megahertz. Mega representation is 10 power 6 hertz. Okay, 2 into 10 power 6 megahertz. And it is terminated with a load impedance means ZL can be written as 60 plus J40 ohms. And the velocity of that is given as V equal to 0.6 into C, where this for a lossless line, or the C can be written as 0.6 into 3 into 10 power 8 meters per second. Right? So velocity means in place of velocity V, we are going to consider 0.6 into 3 into 10 power 8 meters per second. Right? So from the given, all given, then we will be evaluating first thing is reflection coefficient gamma and the standing wave ratio S, and from this input impedance Zin. Right? So to find first the reflection coefficient, the formula is given by here. The first thing, reflection coefficient gamma. So as we know that it is the ratio of the reflected wave field strength to the incident wave field strength, and it is given by gamma for the reflection coefficient of a transmission line is given by gamma equal to ZL minus Z0 by ZL plus Z0, which is equal to, so ZL value is given as 60 plus J40, then 60 plus J40 minus, and Z0 is given as 50 by 60 plus J40 minus means plus 50, which is equal to 60 plus 50 as 110 plus J40 by 60 minus 50 is 10 plus J40, and here 60 plus 50 becomes 110 plus J40. This is gamma. But this gamma can be written as gamma equal to modulus of gamma into e power J5, or phase functions. In order to write this one gamma, then we need to write here, see, first in order to find this 10 plus J40 means if you express this in terms of polar form, R1 at an angle of theta 1 need to be obtained, and in the denominator also if you convert it into polar form, again R2 at an angle of theta 2 need to be obtained by converting using the calculator. We'll convert the given form is expressed in terms of rectangular form. Then to find the magnitude and the phase functions, we need to convert all these two complex variables into polar form. Hence, polar form representation means radius and theta phase angles need to be expressed. For the numerator, it will be given as R1 at an angle of theta 1, and for the denominator, it is R2 at an angle of theta 2. Now, finally, if you find R1 at an angle of means R1 by R2 at an angle of theta 1 minus theta 2. According to the division, the phase angles need to be divided, means we can subtract one from the other. So R1 by R2 at an angle of theta 1 by theta 2. From this, we'll be getting R at an angle of theta. Right? So that R value need to be given is here 0.3523 at an angle of 56 degrees. This is the value of R, and means this is the value of modulus of gamma and e power j for j5. Right? So modulus of gamma value is given, that is 0.3523. Okay. Now from this, the standing wave ratio. So to find the standing wave ratio, the formula is S is equal to 1 plus modulus of gamma by 1 minus modulus of gamma. So from this value, which is equal to previously 0.3523 at an angle of 56 degrees need to be obtained. So this is the value of modulus of gamma, and here it will be e power j5. Right? So from this, modulus of gamma means its value is equal to 0.3523. Right? So 1 plus 0.3523 by 1 minus 0.3523. So if you evaluate the standing wave ratio here, S is equal to, it will be approximately equal to 2.088. 2.088. Generally, we know that the standing wave ratio is ranging from 1 to infinity. 1 is less than or equal to, S is less than or equal to infinity. And if you observe here, this reflection coefficient gamma is ranging from 0 to 1. So that's why always this gamma should be lies between 0 and 1, and standing wave ratio S is lies between 1 and infinity. That's why S is to be obtained as here 2.088 and gamma value need to be 0.3523. Right? So this is the way the first coefficient as reflection coefficient gamma is to be evaluated, and the standing wave ratio S is need to be evaluated. Next is the important one is input impedance. Right? So to find this input impedance, the formula becomes for a lossless one, means Zn is equal to ZL Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. See, in the given formula, in the given one, 30 meters long lossless transmission line is given. Lossless transmission line case, we'll be considering the input impedance equation as Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. So, from the given Z0 is given as 50 ohms and ZL as 60 plus J40. 60 plus J40, Z0 as 50. Right? So Z0 is equal to 50 ohms, ZL is equal to 60 plus J40, and the L value is given as 6 meters and beta. Right? So beta means we will evaluate its value as U equal to 0.6c. Velocity equal to omega by beta to find velocity equal to omega by beta. From this, beta need to be evaluated as omega by velocity. So omega value means 2 pi f, and f value is 2 megahertz as given, that is 2 pi into 2 into 10 power 6 by velocity as for a lossless one 3 into 10 power 8 meters per second. Right? So which is equal to 2 pi means that is 4 pi by 3 into 10 power minus 2. This is the value for beta need to be obtained. So which is equal to means 4 pi by that is 0.04 pi by 3 is to be obtained as the value of beta, right? So beta L means beta into L is equal to 0.04 pi by 3 into 6 can be obtained. Then this 2 gets cancelled. 0.02 into 8 means 0.08 pi need to be obtained as the value of beta L. Now substitute all these values Z0, ZL, L and or else beta are separately beta and L values, or else if you multiply these two, resultant will be 0.08 pi. Now substitute all this into this, then Zn is equal to Z0 means 50 into ZL is 60 plus J40 plus J Z0 is again 50 and tan 0.08 pi need to be written. Right? Why? Because beta L value is to be obtained as here 0.08 pi. Right? So 0.08 pi by Z0 means 50 plus JZL. J into ZL value is 60 plus J40 into tan 0.08 pi. Right, which is equal to then 50 into 60 plus J40 plus J50 tan 0.08 pi by, and here 50 plus J60 and J into J becomes minus J minus and 40 total into tan 0.08 pi, right? So if you evaluate this Z0 value, then finally it will be expressed in terms of again complex form, that is real form as 23.97 and the imaginary one is given as J 71.35 need to be obtained, right? So this is the way input impedance and the reflection coefficient standing wave ratio need to be evaluated with the help of the given sum, right? So 30 meters long lossless transmission line. That's why input impedance equation can be considered as here Z0 into ZL plus JZ0 and beta L by Z0 plus JZL tan beta L. Okay, this is the way input impedance need to be evaluated. And as we know that reflection coefficient gamma can be ZL minus Z0 by ZL plus Z0 and the standing wave ratio need to be as 1 plus gamma by 1 minus gamma. Okay, then next one, a 70 ohm lossless line means here also the characteristic impedance Z0 is given, its value is 70. A 70 ohm lossless line has S is equal to 1.6 and theta equal to 300 degrees. If the line is 0.6 lambda long, obtain gamma, ZL and ZL. Gamma is the notation for reflection coefficient and ZL is the load impedance and Z0 be the characteristic impedance. Right? So to find gamma first, and we require ZL also, right? And S also need to be obtained. That is, using this S value, we can find first reflection coefficient as gamma. And first of all, we need to identify what actually given means. Z0 is equal to 70 ohms and S standing wave ratio S is given, that is 1.6 and theta need to be given as here 300 degrees. If the line is 0.6 lambda means L value is also given, that is 0.6 lambda, right? So and here lambda, then to find the first thing as gamma, we can use this standing wave ratio S. Gamma in terms of this one means S minus 1 by S plus 1, right? So reflection coefficient gamma in terms of standing wave ratio S means gamma equal to S minus 1 by S plus 1, which is equal to S value is given as 1.6 minus 1 by 1.6 plus 1, then which is equal to 0.6 by 2.6. So like this, if you evaluated, then gamma need to be, right? Gamma can be written as 0.228 at an angle of 300 degrees. Why? Because this gamma can be written as modulus of gamma into e power j5, right? So modulus of gamma means its value is 0.228 and the phase function theta need to be given as 300 degrees. Okay. So gamma is equal to 0.228 at an angle of 300 degrees need to be obtained as reflection coefficient gamma by using standing wave ratio as 1.6 and the phase angle as 300 degrees. Right? And if the length of the line is given 0.6 lambda, now from this ZL we are going to evaluate. So Z0 value is there, reflection coefficient gamma value is there. Now using that we can find ZL value. How means? See, reflection coefficient gamma in terms of load impedance and the characteristic impedance formula is given by gamma equal to ZL minus Z0 by ZL plus Z0, right? Which is equal to ZL minus Z0 is 70 ohms by ZL plus 70. Whereas gamma can be considered here, modulus of gamma magnitude is 0.228. Right? So this is given by 0.228 is equal to ZL minus Z0 by ZL plus Z0. By simplifying this equation, we are going to get the load impedance as ZL. So 0.228 into ZL plus 70 equal to ZL minus 70. Right? So 0.228 into ZL plus 70 into 0.228 which is equal to ZL minus 70. We can separate the ZL value and this thing. Then 0.228 ZL, first ZL minus 0.228 ZL which is equal to, then 70 into 0.228 minus means plus 70. So this thing you just consider it as this side and this 70 becomes this side means minus 70 becomes plus 70. Then if you take ZL as common, 1 minus 0.228 which is equal to, and if you take 70 as common, then 1 plus 0.228. Okay. Then from this, see ZL is equal to 70 into 1 plus means 1.228 by 1 minus 0.228. Then from this ZL value need to be obtained as the 80.5 minus J 33.6 ohms. So this is the value need to be obtained for load impedance as ZL. And generally it is an impedance and it can be measured in terms of ohms only. Right? So this is the way the load impedance need to be evaluated with the help of gamma, that is reflection coefficient. Similarly, the last parameter we are going to evaluate is Zin. After obtaining this ZL value and using Z0, we can find Zin. Right? So the formula is given by here. So Zin is equal to input impedance Zin is equal to, that is Z0 into ZL plus JZ0 and beta L by Z0 plus JZL tan beta L. So why we have considered this formula means the given one is line is a transmission line is a type of lossless transmission line. Hence the input impedance of the lossless transmission line can be given by here Zin is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Now substitute all into this. Then 70 ZL value as 80.5 minus J 33.6, 80.5 minus J 33.6 plus J Z0 as 70 tan beta L value. So first separately we can consider it as beta into L, as we know that beta formula is 2 pi by lambda according to the phase constant, beta equal to 2 pi by lambda into L values to be given from the value as 0.6 lambda. Now substitute in place of L by this thing as 0.6 lambda. This lambda gets cancelled, which is equal to 0.12, which is equal to 1.2 pi as the value need to be obtained, which is equal to beta L. So tan beta L means 1.2 into pi need to be substituted in place of beta L by, in the denominator, then Z0 means again 70 plus J into ZL is 80.5 minus J 33.6 into tan beta, that is 1.2 pi. Okay, so if you evaluate the complete equation, then input equation is to be obtained as here 47.6 minus J 17.5, 47.6 minus J 17.5, that is C ohms. Okay, input impedance, no, it is generally measured in ohms, right? So this is the way we can calculate, or we can solve some of the problems based upon this transmission lines. So first, in the first problem, RLGC parameters are given. All the primary constants of a transmission line values are given. Along with this, the operating frequency F is also given. Now we can use all these terms to find the characteristic impedance Z0, that is secondary constant of a transmission line, as Z0 is equal to R plus j omega L by G plus j omega C. By substituting all the primary constants along with the operating frequency, we'll be getting the value as Z0, and it is be measured in terms of ohms. And from that, propagation constant gamma also need to be evaluated. That is gamma equal to root over R plus j omega L into G plus j omega C. R plus j omega L into G plus j omega C. Now here also RLGC values and along with the operating frequency, if we substitute, finally the gamma can be written in terms of real term as alpha and the imaginary term as beta. Now from this we will be consider the attenuation constant alpha and the phase constant as beta. Now the third one we are going to will use, already we have used, that is phase velocity. In order to find this phase velocity Vp, the formula becomes omega by beta, right? So phase velocity or wave velocity can be written as Vp equal to omega by beta, and this is the formulas which we have used in order to solve the first problem based upon the problems on transmission lines. In the second and third problems case, we use the reflection coefficient formula gamma as ZL minus Z0 by ZL plus Z0. In this, ZL and Z0 value is directly given. Then from this we'll be evaluating gamma, and whereas this gamma is ranging from 0 to 1 means this value need to be obtained as in the range of 0 and 1 only. Then from this gamma, standing wave ratio S is also need to be evaluated. The formula for this is S is equal to 1 plus gamma by 1 minus gamma. Okay, so you know the reflection coefficient gamma value. To find the standing wave ratio, the S in terms of gamma is S is equal to 1 plus gamma by 1 minus gamma. So similarly, after this reflection coefficient gamma and the S value, we will evaluate the input impedance of a lossless transmission line. That is given by Zn is equal to Z0 into ZL plus JZ0 tan beta L by Z0 plus J ZL tan beta L. To find this beta and L values are directly given, and beta, in order to find this beta, we can use sometimes beta equal to 2 pi by lambda along with the wavelength if you define, or sometimes lambda, that is wavelength of the transmission line, is lambda is equal to 2 pi by beta. From this we'll be evaluating beta value as 2 pi by lambda. And along with this we will use one more formula as that is reflection coefficient gamma in terms of standing wave ratio, means gamma equal to S minus 1 by S plus 1. So this is the case, the S value need to be obtained here. Gamma value is ranging from 0 to 1, whereas S value is ranging from 1 to infinity. So keep in mind this, or remember for this, reflection coefficient gamma is always ranging from 0 to 1, whereas standing wave ratio S is ranging from 1 to infinity. So if you obtain the values, the range which is to be predefined as gamma value is 0 to 1 and S value is 1 to infinity, then only the exact or accurate values need to be obtained. Then we'll come to know the given values or obtained values are whether right or wrong. So to solve all the problems based upon this transmission line, we will use all the fundamental formulas related to the transmission lines, including all the primary constants and the secondary constants of a transmission line. So all the primary constants of a transmission line means resistance, inductance, conductance and the capacitance, and Z0 and gamma, where Z0 and gamma are said to be secondary constants of a transmission line. Those are characteristic impedance Z0 and the propagation constant gamma. From the propagation constant, we will be evaluating the real term as attenuation constant alpha and the imaginary term as phase constant beta. Sometimes to find the beta, we will use in terms of wavelength formula as beta equal to 2 pi by lambda, or lambda in terms of beta means lambda equal to 2 pi by beta. Okay, so with the help of all these fundamental formulas which are involved in the transmission lines topics, we have solved some of the problems based upon the transmission lines, and internally we have used all the fundamental formulas related to this transmission lines. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.